Welcome, let's get right to it. Today's explainer takes us on a wild ride into a truly mind-bending, futuristic computing architecture. We're stepping way outside the box of traditional electronics today to look at a conceptual breakthrough known as the Ortiz-Inostroza Photonic Non-Nuremberg architecture. If you're a fan of the absolute bleeding edge of hardware design, you are absolutely going to love this.
Picture this for a second. What if computers use stone, geometry, and light instead of standard silicon grids? I know, it sounds a bit like science fiction, right? We are so hardwired to think of computation as microscopic transistors etched into silicon wafers, just pushing heavy electron currents around. But what if we completely replace that silicon with a mix of engineered materials and photonic light? That is the absolute novelty we're unpacking today.
Here's our roadmap. We've got 6 quick stops. First, a new computing paradigm. Second, the non-Nuremberg device. Third, the carbon slate engine. Fourth, the graphene logic core. Fifth, the diamond photonic device. And finally, number 6, rethinking how machines think.
Okay, let's jump straight into Section 1, a new computing paradigm.
Now, what's really fascinating here is the sheer precision of how this started. We're talking about a literal, time-stamped concept statement, July 15, 2026 at exactly 12:04 p.m. CDT. It formally establishes the inventor, Luis Manuel Ortiz-Inostroza, and registers an entirely new device family. This is basically the birth certificate of a completely new technological era, and it marks a huge departure from everything we've previously known about computing.
So what is that departure exactly? Let's hit Section 2, the non-Nuremberg device.
Think about traditional computers for a second. They rely on standard silicon transistor grids. Or, if we're talking about quantum computing, they usually need those freezing cryogenic environments to even function. And in both cases, the logic is just software, code layered right on top of the hardware. But the non-Nuremberg device? Totally different ballgame. The name itself is actually a clever play on the classic von Neumann architecture, signaling a total break from it. These new devices use multi-material bodies. They use light and geometry as the core computing medium. And the craziest part, the logic is physically encoded right into the material itself. So no standard silicon grids and definitely no freezing temperatures.
And that brings us to the engine behind all of this, Whale Logic. The main thing to grasp here is that Whale Logic isn't some software program you download and install. It is the actual routing and weighting rules built directly into the physical design of the material. It tells the signals, whether they're electrical or optical, exactly how to think and move through the system. You are literally building the rules of math and computation into a solid structure.
Let's look at how that structure is actually built. We're moving to Section 3, the carbon slate engine.
This is the first of 3 implementation options, and the material stack for this chip concrete is just wild. We've got shungite and carbon phases handling electromagnetic absorption. Graphene is in there for high-speed conduction. Slate acts as the base, shaping sound and vibration. Boron tunes the carriers. And then, get this, processed food-grade magnesium and zinc to spread power and heat. It's literally a solid engineered stone and carbon composite.
So how does a rock compute? Well, Whale Logic physically routes the signals straight through this dense stone-like body. As the data moves, the actual physical materials are what shape, amplify, or damp the information. It's a physical logic engine that behaves in ways a simple array of transistors couldn't even dream of.
All right, on to Section 4, the graphene logic core.
The second variation introduces a fascinating layer of complex geometry. We still have our slate, boron, magnesium, zinc, and carbon doing the heavy lifting for support and shielding, but the real stars of the show here are the ultra-thin layers. Graphene acting as our super-fast conduction layer paired with molybdenum disulfide, or MOS2. The MOS2 is kind of the secret sauce. It creates these semiconducting islands that allow for quantum-sensitive switching.
Now watch how this comes together. First, a specific geometry, the famous flower of life pattern, is literally drawn right into that graphene and MOS2 layer. Second, that pattern isn't just there to look pretty. It is the circuit. Every petal, every single intersection acts as a specific logic or memory point. And third, Whalic logic dictates how signals branch and delay as they travel through this flower. It behaves less like a classical processor and, well, actually, scratch that. It doesn't behave like a processor at all. It's much more like a 2D thinking fabric or a brain map.
Okay, Section 5. This is the absolutely stunning third option, the diamond photonic device.
For this one, we take that same bulk composite of slate, carbon, and metals we just talked about, but we slap on a crucial new element, a top surface made of diamond,
or diamond-like carbon. And the kicker? That same flower of life pattern is written directly into this diamond surface using a cold purple or blue laser.
The way this thing processes data is straight up magic. First, the graphene structures at the edge take your standard electrical input and convert it entirely into pulses of light. Second, those light pulses dive deep inside the diamond flower of life network. And third, the actual math, the computation, happens just by bending, splitting, and combining that light inside the network. Because we're using light instead of heavy electrons, heat is basically a non-issue. Plus, the microscopic defects in the diamond can actually hold quantum-like states, meaning this thing can compute incredibly fast.
Let's pull all of these threads together in our final section, number 6, rethinking how machines think. When we line these three implementations up side by side, it really paints a clear picture. The carbon slate engine relies on engineered stone and thinks by physically routing signals through a dense body. The graphene MOS2 core uses ultra-thin layers and thinks by tracing signals through a 2D flower pattern. And the diamond photonic device, it thinks by literally bending light pulses across a diamond surface. Three totally distinct builds, but they all belong to the exact same revolutionary family.
The big takeaway here is that this is a massive system-level shift. We aren't just figuring out how to make a silicon chip 10% faster or a little bit smaller. By moving to this multi-material, geometry-driven architecture, we are essentially taking the thought, the logic, the decision-making, and baking it directly into the physical material itself. So I want to leave you with a question to chew on. If computing really does shift away from those rigid binary silicon grids and moves toward these thinking fabrics made of engineered stone, geometry, and pure light, how is that going to change our relationship with machines? Will they start feeling a little less like cold, calculating boxes and a bit more like an extension of the natural world? It's definitely something to ponder as we look at the future of hardware. Thank you so much for joining me on this explainer today. Keep questioning, keep learning, and I'll catch you on the next one.